Alrighty, welcome back to the C++ course. This is chapter 16 called Exceptions and Templates. Two very, I would say, unrelated topics, but two very important topics nonetheless. Both exist in other programming languages. Of course, how they're expressed in C++ tends to be a little bit little unusual or maybe a little different than what you would see in a more modern approach to these topics. So, we're going to take a look at what exceptions are, how to write them, what's the point of an exception, and then the rest of the lesson is going to be on templates. So we're going to discuss function templates, class templates, and then class templates and inheritance. And just to kind of get the juices flowing a little bit, I would say when somebody says the word template, you probably have some idea of what we're talking about floating around in your mind somewhere, but that probably is not what we're going to be talking about today. Take whatever notion you have about templates and throw it out the window, because when we talk about templates in C++, what we're really doing is talking about something called generics in other languages. And we've actually used templates when we made use of things like the C++ STL, namely the vector class. If you remember, vectors are basically a dynamic list of objects. And you can put whatever you want to in a vector, really. You're not limited to just saying, okay, here's a vector of integers. I can only put integers in a vector. If you have a vector of ints, you can only put ints in it, but you can also create a vector of double or a vector of char or a vector of strings. You're not limited to a single data type, and certainly you don't have to rewrite the vector class for every single data type. And so when we talk about templates, we're really talking about reusable code that can work across a variety of data types, not just one specific type. A simpler example may be like a square root function or a square function, where you can pass in an integer, you can pass in a decimal, a fractional value. You're not limited to just one single data type. And certainly, again, like I said, you're not expected to rewrite the square or square root function for every single type of data that you may want to operate on. So that's what we mean by templates. Keep that in the back of your mind as we move forward. Okay, so what is an exception? And again, virtually all languages support this idea of an exception. It is a value in an object that indicates that an error has occurred. Okay, big deal. You might be thinking, because certainly we've had errors in our programs before, and usually we're kind of talking about like user input error, generally speaking. And we've tried to handle that kind of error as gracefully as we could in the past, usually with something like an if statement, where if you're saying something like, do you want to input some more data, yes or no, we can check to see if the data that the user entered is a Y or an N, make sure it's not numeric, things like this. And that's perfectly acceptable. That's a great way to check for valid or invalid data. But an exception is a more robust way, I would say, to check for valid or invalid data. And it's a concept that's built right into the language. This is like a part of the core C++ language. And so it's built in, it's there, we might as well use it. Again, it indicates that an error has occurred. So when an exception, this is like an exception to the normal flow of the program, is kind of what we're getting here with the term exception. The program runs as expected, except in this case, and if this thing happens, here's what we're going to do. So when an exception throws or occurs, the program either terminates or jumps to a special section of code for handling the exception. So not only are we going to be checking for specific types of errors, but we need to tell the program what to do if those specific types of errors are encountered. So the exception is basically the check. The exception handler then is what to do if that check happens, if that thing happens that we're checking for. So we check to see if it happens, and then we handle what happens if it does occur. So some keywords here. These are all C++ reserved keywords. So really three big ones here when we're talking about exceptions. We talk about throw. We talk about throwing an exception is kind of how people talk about this, followed by an argument, which is used to signal an exception. This is what we say when we're checking for the problem, checking for the error, or throwing the exception. Along with that, we have something called a try-catch block. Okay, a try block is surrounded by curly braces, and it's used to invoke code that may throw an exception. So in the code that you're checking the exception for, you should use a try block to surround all the code that you think the exception may occur in, if that makes sense. You can only use exceptions if you're inside of a try catch block. So try is the code that you're just kind of, inside of the try block is the code that you're just kind of running, and it's the normal flow of the program. When you say you're trying code, you're saying that, okay, I'm doing this execution, but there may be something that goes wrong in here. We may have to throw an exception. So the throw typically occurs in the try block, and when we throw an exception, we have to catch it. And the catch is also surrounded by curly braces. That's what happens when the exception occurs. That's what we do when we process it. So it's used to process exceptions thrown in a preceding try block, and it takes a parameter that matches the type of exception thrown. So based on the type of exception or type of error that you're checking for, you will get for free, kind of out of the box here, a parameter in your catch block that may contain information about the error that was thrown. Okay, and then it's up to you, like I was saying, to do something with that information. You log it to a file, save it to a database, display the information to a user, whatever you want to do with that information, up to you. But the cool thing and the important thing that I'm not even sure if the PowerPoints get into is that when you encounter an issue in your code, a runtime error basically, a typical example is like a divide by zero. We all know from our basic math classes that you cannot divide something by zero. It's like a mathematical anomaly, I guess. So our code, if it encounters that, and we aren't using a try-catch block, the program will crash. The program will crash and throw an error message up to the console window saying, hey, I don't know what to do. I'm trying to divide by zero, so just crash, end of program. And the user experience is very, very bad. But with a try-catch, if we catch a divide by zero exception, we throw up an error message, and then the program keeps running as normal. So what I always say is exceptions are a more sort of graceful way to handle errors when your code is running. It's not going to crash the program. Instead, we throw an exception and handle it gracefully. The program won't stop running. Okay. Throwing an exception, so code that detects an exception must pass information to the handler. This again is done using a throw statement. So here's kind of a manual way to throw an exception. Throw string emergency. So the string emergency would be passed then down to the catch block and processed however we're going to process it. You can also throw an integer or throw any kind of data you choose. In C++, the information thrown by the throw statement may be a value of any type. So these are obviously pretty basic data types, but you can throw any type of data really. Okay, so say we throw an exception, how do we catch it? So a block of code that handles the exception is set to catch the exception, and it's called the exception handler. And it looks like this. So it's a keyword catch followed by that parameter that we were talking about on the previous slide. This can be almost anything, any data type you could want, and the name of the parameter is basically up to you. I would say that the most common thing to call this parameter would be like EX or even E in some languages. EX for exception. And then, so this would change too. You could just print the exception. So an exception handler is written to catch the exceptions of a given type. For example, this can only catch exceptions that are string objects. So you're limited to that type of data. And the block of code, again, is called exception handler. We're handling the exception that we've thrown. Another example, so this is just passing in an int x. So maybe the x integer stands for some kind of error code that was set up by the programmer, and that means something to the person running the program. And then notice here, instead of doing a straightforward cout, we're doing a cerr instead just to make it a little more obvious, a little more verbose, that we're printing out something that is going wrong. This will catch an exception of type int. Okay, connecting to a handler. Finally, this would be like a full example, I would say, of a try catch. So every catch block is attached to a try block. So you cannot have a catch without a try. These two go hand in hand, and is responsible for handling exceptions thrown from that block. So inside of your try block, again, this is just any old code you may write, any kind of if statements or arithmetic or anything that you're doing. The main bulk of your program would go in here. Then if something goes wrong there, the catch block will be run. Okay, so try is the normal execution. Catch is how you're going to handle any errors that may occur in the try block. Surrounded by curly braces, just like we mentioned before. Execution of catch blocks. So the catch block syntax is similar to that of a function, and a catch block is a formal parameter that is initialized to the value of the thrown exception before the block is executed. So this should have a value. If we're throwing a exception up here in the try block, we'll also want to make sure that we're throwing a char for a parameter. So that char will come down here and we can access it and do whatever we will with it. Again, maybe the char is some special error code that's been established by the programmer or whoever's setting up the specs for this program. Got that. So an example of an exception handling is code that computes the square root of a number, and it will throw an exception in the form of a string object if the user enters a negative number. So if you remember back from your high school math classes, you know you can take a square root of a negative number, but then you get something called an imaginary number back. A bit esoteric, I know, but for our purposes and our simple examples, we're going to assume that if you want to take the square root of a number, it must be positive, or I guess 0. We're not going to delve into the strange world of imaginary numbers. Again, just for this example, we're going to throw if the parameter to the square root function happens to be negative. So here's what that might look like. Check it out for a minute. We've got our int main, we've got our try catch. Inside of our try block, we've got a double X. We're going to enter, or we're going to see into that double X. If X is less than 0, we're going to throw, there's that key part there, throw a string and pass in basically just a simple error message called bad argument. So if that is true, and remember, this is all in a single line, that's okay. Maybe if you're more comfortable seeing it like that. Okay. But regardless, so it's just a simple if statement, then we're going to throw. Okay. Otherwise, we're going to continue on and just take the square root of X. But if we do happen to throw this string, we're going to come down here to our catch. This bad argument text will be passed down into the string str, and we'll print that out and then finally return 0. So I actually don't know what would happen. This square root function is just one that's built into the C++ math library. I don't know if it supports taking the square root of a negative number or not, but basically we've checked in this case to make sure that it can handle that situation gracefully. And then we'll just print out to the user that they've provided a bad argument. And you can also do, other things, other checks, like make sure that the user has entered a number, make sure that it's properly formatted, things like that. So flow of control. So the computer encounters a throw statement in a try block. Again, if you want to throw, you must be inside of a try. The computer evaluates the throw expression and immediately exits the try block. So as soon as it hits the throw, the control of execution is going to transfer down to the catch. But again, all this must be inside of a try. And so the computer selects an attached catch block that matches the type of the thrown value, places the thrown value in the catch block's parameter, and then executes the catch. Finally, enough chatter. Let's check out page 1003 and get our hands dirty. A lot of background information, especially when we have 3 or 4 new C++ reserved keywords. yeah, we got to take some time to talk about them first. And I already have created a new solution for this chapter. I went ahead and tested some things beforehand to make sure that things would be working properly. If I can get my window resized here. Because the next section on templates is a little kind of, you're dealing with multiple files in some cases when you're dealing with templates. And as we know from a couple lessons ago, sometimes that can cause runtime issues. So anyway, pretend like testing and testing 2 and testing 3 don't exist. We'll focus in on 16-1.cpp. In fact, I'm going to right click this tab and close all but this. Get rid of those other open tabs. Okay, this simple program illustrates exception handling. So we include IOStream. We're going to include string. We're going to use our standard namespace like always. I always try to mention, like, if things that we're talking about require extra includes, try, catch, throwing exceptions do not require extra includes. These are built into the C++ language core, again, like it is in most other languages. And I should say most other languages use the same syntax and the same keywords. Everybody kind of just sticks with the try, catch, throw sort of paradigm. Okay, what do we got here? We got a function prototype. It's going to return a double called divide, passing in a double and a double. I've taken a liking to, when I'm prototyping my functions, I've taken a liking to not having to name my parameters to these functions, but instead just providing data types. I think that's a pretty handy way to do this prototyping, where in the past I've always given these guys names, double X, double Y, but saves a little time, saves a little creative energy if we don't have to come up with imaginary names for parameters that don't matter anyway. So double divide. Let's see what that function does. Can probably guess. Okay, double divide, double numerator, double denominator. Okay, we're going to do a check here. We're going to say if, here's that divide by 0 check. If denominator is equal to 0, we're going to throw a string, error, can't divide by 0. Cool. Else, we'll just do the normal division, return numerator over denominator. Of course, we would never really need to write a function like this, just for demonstration purposes. Obviously, C++ has a built-in division function. We're using it here inside of our divide function. By the way, this is kind of called a wrapper function. If you're creating your own custom function where all it's doing is like wrapping up another either built-in function or a function written by somebody else, maybe just providing a little extra error handling or functionality, call that a wrapper function. So our divide function basically wraps the built-in C++ division operator. Good enough. Let's head back up to main and let's create some ints. So int num1, num2, double quotient, cout, enter two nums, cin to num1, num2. And here is where we will enter our try catch. Now, what I like to do, as soon as I write my try, and notice that Visual Studio provides me with those curly braces, I like to make sure that I jump down here and immediately write my catch statement. In this case, we're going to catch a string. I'll just call it EX for consistency. If we happen to catch that EX, we're going to cout just whatever it is. Cout EX. And we know that our EX is going to be this error string that's down in our divide function. Okay, so we're going to try quotient equals a call to the divide function passing in num1 and num2, and then just cout quotient is quotient. And yeah, what we'll want to do is jump down here, cout. So they're just showing us here the flow of the execution, end of program, to demonstrate that if we would happen to run that catch block, that the program's not done here. We're not done as soon as we print out this EX. It's going to keep going. And then again, that's one of the benefits of using try-catch. Yeah, there was a problem in the program, but we're not wrecking the whole program. It's not going to crash on us. We're just going to catch this error, do something with it, and then continue on until we return 0. Okay, let's set active, and let's see if we can catch. Let's see, they're like 12.2, good, quotient is 6, end of program. New line would have been handy, but oh well. How about 12.0, can't divide by 0, end of program. Good enough. So that's your basic try-catch. What about uncaught exceptions? So, like, obviously there's a lot more that can go wrong in our programs that maybe we can catch. So what happens then? So an exception may be uncaught if there is no catch block with a data type that matches the exception that was thrown, or it was not thrown from within a try block. And in that case, the program will terminate. So you can also throw an exception class, and an exception class can be defined and thrown. A catch block must be designed to catch an object of the exceptions class, and the class object can pass data to the handler via the data members. All that sounds a little bit abstract, so let's check out a class actually that they've given us on page 1005. And this class is called intRange.h, and we're going to rely on that, I believe, in the next hands-on. So I've got it handy down here, right here, intRange.h. We're going to copy some of that code into our Visual Studio project here in a minute. But what does it do? What does intRange do? Not much. Again, it's just for demonstrations mostly. So we've got some private data members. So we've got an input, a lower, and an upper. We've got a public exception class. So check that out. So it's a class called outOfRange built into my intRange class. It's got an empty class declaration. So it is a class keyword, name of the class, open, closing curly, and a semicolon, just like the intRange class, only it doesn't have anything in it. So intRange is our constructor. We pass in a low and a high. And we assign those to the private data members. Then we get input. We're cin into input. And then we're just checking to see if our input is less than lower or greater than upper. Then we're going to throw that out of range exception and then return the input. Any more explanation needed here? Yeah. Instead of throwing a string or some value of a primitive type, this function throws an exception class. Notice the empty class declaration that appears in the public section. Then notice that the class has no data members. The only important part of this class is its name, which will be used by the exception handling code, and then check out the if statements. Okay. Then yeah, let's jump right into 16.2 and make sure that we can include that header file. And I've come up with a better way, I think, to deal with using these external header files. Let's first add our new project EX 16.2. And what I'm going to do is I actually have intRange.h. No, it's not. I'm going to open that up in just a simple text editor. Right here. And I'm just going to Control A to select all. Notepad++ is great, by the way, if you just need a quick and dirty text editor with great theming and syntax highlighting for almost any language. Notepad++ is great. Definitely a step up from the built-in Microsoft Notepad. So there's intRange.h. What I'm going to do is right-click on my header file section, add new item. Up here, I'm going to select header file, and I'm going to give it the same name as in 16-2, so capital I, capital R, intRange.h. So intRange.h. Add it, and then inside of intRange.h, boom, copy paste the whole thing. So that's good. That's a quick and dirty way of including external code into this project. Let's check out 16-2. Let's set this as active. And let's just make sure that our include actually works. So include int range.h. Good. Everything seems happy. Using space std. Good. Let's go ahead and create a new int range object. Int range, passing in lower is 5, upper is 10. Int user input. Let's see. Yeah, that's fine. Cout. Enter a value in the range 5 to 10. And then we'll do our try. We'll jump down here to our catch right away. Here. User value or user input equals range.get. Where's my, oh, I didn't name it. Int range called range. There we go. Range.get input. Good. And then cout. You entered user input. End line. I forgot to do my catch already. Catch. Okay, we're going to catch. Check this out. So int range : out of range. That's that nested sort of class name that we have inside of the int range header file. So if we catch that, I'm going to cout out of range. And then if we do happen to catch that, we're going to keep going. End of program, new line, return 0. Okay, let's check out the sample run of the program. So if we enter a value that's outside of that range, we're going to throw that out of range class, and then that's the end of the program. Okay, I would say that's a more robust way to throw exceptions. You can think of it like, if we go back to intRange.h, yeah, we're not doing anything inside of this class, but it is a class, so we can do any number of things inside of that and make it a very, very robust way to handle exceptions versus just throwing a regular old primitive data type or a string or something. Cool. Okay, multiple exceptions, and I think this next example, yeah, we'll just do a read-only of the next hands-on, but you can throw multiple exceptions. Multiple catch blocks can be attached to the same try block. The catch blocks should handle exceptions of different types. So the syntax looks like this. We've got a try, then a bunch of statements. We can catch an int called that, a string called that, and then a double called that. And if we take a look at int range2.h, kind of see what that looks like. Yeah, so we've got a couple exception classes in here, same class, except for we've got a class called toLow and a class called toHigh now. So you can probably guess when we're going to be throwing those exception classes. If we have a value that's entered that's too low, we'll throw toLow. Otherwise, we'll throw toHigh. And then if we page forward here a little bit, yeah, right here is that implementation. So if we see into input and input is less than lower, throw the toLow, otherwise throw toHigh. And I want to see, is that in the get input? Yes, it is. So those are thrown basically, so notice how those are thrown within the class themselves. We're not throwing in main anywhere. And then that's kind of the common pattern that is followed in the professional world of C++ coding. We don't really, you can certainly throw exceptions manually inside of main, but most of the time the throw statements are going to be built into the class themselves. And if you notice here in our int main, we're catching two different things. Here's that catching multiple values thing, but we're not actually throwing it anywhere. So the throw happens in get input. If that happens to throw, well, then this catch is going to be run. So here's an example of the throw is not in the same file as the catch. The throw is in get input, which is in int range2.h, but we're catching it inside of main. So try to take some time and wrap your head around that, because that is a pattern that shows up all the time in the real world. We're throwing in the class, but we're catching inside of main. And you can see a sample run here. Okay. Okay, exception when calling new. So this is kind of a specific, I guess, case of throwing exceptions. So new, remember, is that way of dynamically allocating memory at runtime inside of your program. And so if new cannot allocate memory, it throws an exception of type bad alloc. So you must include new to use bad alloc. And you can invoke new from within a try catch and then use a catch to detect that memory was not allocated. Use your imagination, and hopefully it's not too challenging to come up with a reason why memory is not allowed or able to be allocated. Picture a scenario on maybe a very low-powered, low-horsepower computer where you simply don't have enough memory inside of the machine to do any kind of alloc or dynamically allocating new memory. So that's just a kind of a specific example. We're defining an exception handler. So the compiler looks for a suitable handler attached to an enclosing try in the same function. If there's nothing there, it terminates execution of the function and continues the search for a handler starting at the point of the call in the calling function. And here's int range 3. Again, we'll just take a read-only approach here. Int range 3. And let me back up actually. I want to focus on the bottom here. So here's the exception class. In this case, the class isn't empty. So the class is called out of range. It does have a public section. Inside of that public section, it's got an int value. And it also has a constructor where you're going to be passing in an int called I and then assigning that I to the value property. And then down here, so when we're actually doing the throw, we're checking to see if it's within range. If it's not, throw an out of range exception passing in input. So this is a way to kind of provide more data into that class-based exception handler. And certainly in example 16.4, so enter a value in the range. Get input, remember, is where the throw happens. If we would happen to catch an out of range exception, this is how we do it. Remember in the previous examples, we didn't have that EX parameter attached to the exception class. Here we do. This is more or less just an example of the syntax for using it. So now we have that EX, which we know from the implementation contains the value that the user tried to enter. If it's out of range, we have that value now and we can report that back to the user. So enter a value between 5 and 10. If you enter 12, it says the value 12 is out of range. So a little bit more detail providing back to the user why the thing that they tried is no longer working. This is 16.4, good. Let's see what 16.5 has in store for us. Oh yeah, here's the bad alloc thing. Just an example, I guess. I am curious how this is actually going to work. So the new operator throws a system-defined type bad alloc if it's unable to allocate storage. It attempts to allocate an array of 2 ints using the new operator. If it fails, the resulting bad alloc is caught and the attached catch is terminated with an appropriate error message. If it succeeds, the program proceeds, blah, blah, blah. I don't think this is actually going to do anything though, because you have to try to throw this exception. So just take this as an example of what that would look like. Okay. Something called unwinding the stack is talked about within the context of exception handling. So an unhandled exception propagates backwards into the calling function and appears to be thrown at the point of the call. It looks like it's thrown at the point of the call, but as we know, the throw actually occurs in the exception class, not inside of, in our case, int main. So the computer keeps terminating function calls, tracing backwards along the call until it finds an enclosing try block with a matching handler, or it propagates out of main, which terminates the program. This again is called unwinding the call stack. You can also do nested exception handling, so try blocks can be nested in other try blocks. Here we have a try and then process data. That's a function call that contains its own try block, and there's nothing wrong with that, just like nested ifs or nested loops. You can also rethrow an exception. Sometimes a handler may need to do some other tasks, then pass the exception to a handler in the calling environment. Throw with no parameters can be used within a catch to pass the exception to a handler in the outer block. So you can just use a plain old throw in this case. Okay, shifting gears to the second big idea of the chapter, function templates. Hopefully exceptions and exception handling kind of make sense. It's hopefully not that mind-blowing of an idea. Again, all languages contain a way to throw exceptions. All right, function templates then. So again, shifting gears, throw whatever idea you have about the word template out the window because it's probably not that. So a lot of times you might think of like a Microsoft Word template where you can click and it's got a bunch of like graphics and fillable text fields where all you have to do is maybe swap out your own graphics or type in your own text, maybe change some colors. That's kind of what most people think of when they think about templates. In C++ though, a function template is more of a pattern for creating a definition of functions that differ only in the type of data they manipulate, also known as a generic function. Okay, so it's a pattern. Generic, as I mentioned earlier, is what other languages call this idea. I think Java calls it generics. I think C# does as well. They can be better than overloaded functions since the code defining the algorithm is written only once. That's the key here. We write the function once and it can operate on a variety of different data types. That's huge. So here's an example. Two functions that differ only in the type of data they manipulate. So we've got two swap functions. We've got one that uses an int, one that uses a char. So in the past, you may have thought, hey, yeah, swapping is great, but it only works for integers. What if I need to swap two chars or two strings or two other data types? I'd have to rewrite it with just those data types. Well, that's not the case. This is kind of a non-templated version. There's some keywords and things we have to do to make it templatized, if you will. But this is kind of the problem that we're trying to solve. Two functions differing only in the data types. So this is how we could convert it to a template, a swap template. The logic of both functions can be captured with one template function definition. So there's a lot of scary syntax with this. It does look a little bit strange. So swap again is a template function. We want to turn this into a template function. So above it, we need the keyword template, followed by a less than or angle bracket and an opening angle bracket and a closing angle bracket. That's one of those things I would just type in both of those right away to make sure you don't forget them. And then inside, use the keyword class space some usually uppercase letter T. I'll just put it that way. If you're working in a language that calls them generics, usually they use like an uppercase G, but we're in C++, so we're using an uppercase T. This is like a placeholder data type. That's how I want you to think about this T. Class T is a placeholder data type that could be really any data type. So then in the swap sort of header, the signature, we're not referring to specific data types anymore. We're referring to an address of T, whatever T is. Maybe T is an integer, maybe T is a char, maybe it's a double or a float. Whatever T is, pass me an address of type T. Two of them, in fact, because we've got a swap function, so we need two things to swap. So thing one is an address of type T, thing two is an address of type T. Parameters are called X and Y. Then down in the body of the function, we've got a temporary variable of type T. We're getting super abstract here, super generic. There's no concrete data types here. So we've got a type T called temp equal to whatever is passed in for X. We're assigning X the value of Y and then Y the value of temp. Your standard swap algorithm here, that shouldn't be surprising, these three lines of code. But the only difference is we're using type T instead of concrete data types. This is a good example of the syntax of how to turn a function into a template. So using a template function then, so when a function defined by a template is called, the compiler creates the actual definition from the template by inferring the type of the call parameter from the arguments. So if we pass in two integers to swap, the compiler behind the scenes is like redefining our swap function to use integers. That's kind of why they're called templates. The compiler uses that code as a template, not so much us as programmers. The compiler saying, hey, he passed in or she passed in two ints. I'm going to create a version of the swap function that operates on int. The code makes the compiler instantiate the template with type int in place of the type parameter t. So a few notes here. So a function template is a pattern, as we said earlier. No actual code is generated until the function named in the template is called. That's kind of interesting. So that code it's not actually being materialized, if you will, in the compiler until that code is called, because the compiler needs to know what types of data to create the function on. Function template uses no memory. When passing a class object to a function template, ensure that all operators referred to in the template are defined or overloaded in the class definition. That would be, for example, if we had a silly example, but instead of swap, say we had an add function that added two numbers together of any data type. Well, when we actually go into the body of the function and do the adding, we have to make sure that the two things are able to be added together, that they support the plus operator, basically. Certainly ints, you can add two ints together, you can add two doubles together, but if I tried to pass in two like player objects, well, in the player class, we would have to make sure that we've overridden or overloaded the plus operator so that the compiler knows what we mean when we want to add two players together. That's still some work we have to do on the back end to make sure that the things that we're adding know how to add themselves together. Most of your standard data types will do that, but if you're passing in larger objects like players or worlds or levels, you have to make sure that those things know how to add each other together. What else? So that's kind of what we meant by this point. All data types specified in the template prefix must be used in the template definition. Function calls must pass the parameters for all data types in the template prefix, and the templates can be overloaded, but they need different parameter lists. And just like regular functions, function templates must be defined before being called. No surprise there. Let's get our hands dirty here with a little bit of template syntax on page 1014. And let's see what we need to include here. Nothing, actually. That's good. So 16.6. Add new project. And I would highly encourage you, even if we don't necessarily go and hand type all of these examples, to do it on your own. Anytime we encounter some new syntax, especially with templates, it's useful to get a feel for how it's actually written. Include IOStream, include IOmanip, my favorite library. Not really. Using namespace std, and let's try to write a template function. Okay, this guy's going to be, here's a keyword, template. Remember, here's the opening angle bracket, closing angle bracket inside. We're going to have the keyword class followed by T. And I think you can use whatever letter you want to there, but most people just stick with T. Okay, so that kind of labels my function now. So I'm going to have a square function that accepts a type T called number, and it also is going to return a type T, where we don't know what T is necessarily, but we know we're going to accept a T and we're going to return a T. Again, maybe a T is an integer, maybe a T is a float or a double. Maybe a T is a player, but the player, if you are passing a player object in, must know how to multiply itself. Okay? Chances are a player doesn't know how to multiply itself, nor would it need to, but if you wanted to pass in a player object to the square function, it must override the multiplication operator. Okay? That's all that this little template function is. So we're going to see out set precision 5, see out, give me a num, int val, cn val, cout square is call square, passing in val, good. Now let's get a double and compute its square. So let's create a double val2, cin to val2, cout square is square val2. And the compiler likes this too. Because it is a template, we can pass in an integer like val. We can pass in a double like val2, and the compiler is perfectly happy. It knows how to handle the idea of C++ templates. Now, without templates, of course, we would have had written the square function twice in this case, once for an integer and once for a double. And then you can see a sample run of the program there. Pretty powerful idea here. So where to start? So templates are often appropriate for multiple functions that perform the same task with different parameters and data types. Develop functions using usual data types first, then convert to a template, add the template prefix, converted data type names in the function to type parameters, i.e. t types, in the template. So what they're saying here is if you have a hunch or an inkling that a function that you're writing may benefit from sort of templatizing it, just write the function using a very, very basic data type first, like an integer or a float or a double, and then come back into it later when you have the need to make it into a template and convert it. And basically all you're going to do is replace all your concrete data types with that T data type that we were just talking about. 1017, let's see what this hands-on has for us. Looks like we've got, the swap here. We'll just talk through this one. Demonstrates the use of the swap function template. So we've got IOStream, string, and algorithm. Algorithm contains its own implementation of swap. And certainly if you were to peer into the algorithm library, you would see templates everywhere, because we know that the swap function is able to swap values of multiple different data types. So here's a char, first char, second char. We can see into that. We can call swap using first and second char, print it out. We can create two ints, enter them, swap them, no problem. We can even pass in two strings. So string first string, string second string, call swap on first and second string. Life is good. I just called swap on 3 different data types because swap inside of the algorithm library uses templates. 1018. See what's in store for us here. So using operators and function templates. This one's pretty good. Let's do 16-8. Let's type that out. Lots of good syntax here. Syntax heavy example. 16-8. And life is good. Let's include string. Let's using name space std. Okay, template. Open close angle brackets class of type T. All right, it's going to, whatever this function is, it's going to return a type T. We're going to call it minimum, passing in a T array, check that out, and some integer called size. So perfectly fine to use the generic type T in the context of an array. So whatever type of array is passed into this function will be just fine. More or less, I'll come back to that statement, I'll put it that way. So T, type T called smallest equals ARR at location 0. Basically, we're trying to find the smallest value in the array. We're going to loop through it. So for int k equals 1, because we know we've got the smallest theoretically stored in 0 already, and that's fine. K is less than size, k plus plus. If ARR at location k is less than smallest, then we're going to say the smallest is now equal to the array at location k. So I hope that this little simple minimum finding algorithm is okay. We've covered it in other lectures, so we're going to return the smallest. I'll leave it up to you if you need a refresher of how this works. Again, we've covered it in other lectures, but the key with this is that because this is type T, all the values in the array are of type T, and the key is here, this less than sign. Whatever type T is, If you pass in an int, if you pass in a float, if you pass in a double, whatever that type t is, it must know how to compare itself to something else. So if we pass in an int, certainly an int knows how to see if it is less than another int. But if we passed in a player object, unless we've overridden the less than sign in the player class, it's not going to know what to do. And in this case, maybe it makes sense to override that. Maybe to say that player 1 is less than player 2 means that player 1 is of a lower level, like he has less experience points than player 2. Might make sense to override that. And if you did that, you could pass an array of players into this minimum function, and it would work just fine. The key is to make sure you've overridden the less than symbol here. I'm going to leave the int main to you. Take a peek at it over here. So we have an array of ints. We can find the smallest number in an array of ints. We can create an array of strings and find the minimum of an array of strings just fine, because a string knows how to compare itself to another string. No problem. Function templates in C++11. So as of C++11, the keyword type name may be used instead of class in the template prefix. So I guess they figured that using this keyword makes more sense than using this keyword. I would tend to agree, actually. I think it's kind of strange that they use the class keyword here for t. So you can instead use template, and then in your angle brackets say of type name t instead of class t. We've already seen, obviously, that class t works just fine, so you can say type name t as well. I think to test that, let's go to 1019. Yeah, there's nothing really remarkable going on here. Illustrates uses of function templates. Yeah, you can read through that one on your own, but for me, I am curious. Echo in reverse. Yeah. I am curious if we can just go ahead and, like, instead of saying class T, where's my active project? Go back to 16.6. Yeah, let's try. Instead of saying class T, let's say type name T and see if that guy works. If I activate this project, just to verify, yeah, give me 3 squares 9. Whoops. Okay. Oh, right. We needed 2 different numbers, 1 integer, 1 double. Regardless, that's not what I was checking for. Just making sure that type name works instead of the class keyword. Works just fine. And it makes more sense syntactically, I think. 1020. Demonstrates overloaded function templates. All right, so what are we doing here? I'll leave the typing of this up to you guys, but we have basically 2 different versions of a sum function. Okay, same name. So that's the overloading part of this. It's 2 functions that have the same name, but have a different parameter list, and they both are templates. So this sum is a template of class type T that accepts 2 T's. This one is a template of class type T that accepts 1, 2, 3 T's. And again, the key in the function body is that whatever type T is passed in must know how to add itself. That's the key. Any type T must know how to add itself to another type T. But this is just a simple example of, again, overloading. We've got a sum that accepts 2 and a sum that accepts 3. You could do the ultimate sum function by passing in maybe an array of T's. Then you can just iterate over that array and sum however many elements you have in your array. All right, the last big idea here of the lesson is called a class template. So we started with function templates because they're a little bit smaller in scope, a little bit easier to wrap your mind around, but you can also have a class template. So it's possible to define templates for classes. Such classes define abstract data types. Classic example of this is the vector class that we've used throughout the semester. Again, a vector can store a list of integers, it can store a list of chars, a list of strings, a list of whatevers. So it is an example of a class template. Unlike functions, a class template is instantiated by supplying the type name, like int, float, or string, at the object's definition. So here's two classes. Here's a class used to join two integers by adding them. So it's a class called joiner. It's got a public int function called combine, int x, int y, returns the sum. Here's a class used to join two strings by concatenating them. String combine, same idea in both classes, same code, except the data types are different, and certainly the result will be different. So strings know how to add each other, and that just means they concatenate. Ints know how to add each other, and that means they get their sum. So each data type has its own idea of what it means to add itself. Okay, so this is not a class template. This is two classes that need to be templatized, I would say. Here's what that would look like in the template version. A single class template can capture the logic of both classes, written with a template prefix that specifies the data type parameters, and it looks like this. So if we know that our class is going to be a template class, again, just like functions, we slap the template keyword on top of it, followed by angle brackets and class type T. Then in the class, in the public section, we have our combine function that's going to return a type T. It's going to accept a type T called X and a type T called Y. It's just going to return the sum, or whatever it means, to add X plus Y. Very, very similar syntax, similar idea, only we're operating at the class level now, not at the function level. But the ideas are exactly the same. So now, this I guess is a little bit different. If we wanted to actually create an instance or create an object of those classes that are defined as templates, you specify the actual parameters for the data types like this. So if we want to create a new joiner, an instance of the joiner class, a joiner object in other words, we say joiner JD, but we need to say what type of data it's going to be instantiated to. So here we're creating a joiner of type double. Here's a joiner of type string. And again, you're used to this syntax because we had to do this when we would create new instances of vector objects. You can't just say new vector. You've got to say, I want a new vector of type string, a new vector of type char. So here we just kind of did that ourselves. We created our own custom implementation of that idea with our joiner class. And this will just print 8.0 and then print hi ho. So we've got simplevector.h. Yeah, let's take a peek at that. We'll do a couple examples and then we'll call it a day. Simple vectors right here. The key here is there's our template keyword, class type T. And this is sort of just our own kind of implementation of the built-in C++ vector class, but like it says, it's simple. We've got our pointer and we've got our array size. We've got some constructors here. We've got a copy constructor. We can return the array size. An array is being used behind the scenes as our data store for our simple vector class. Here is where we are overloading the square bracket operator. So we're going to be able to use our simple vector class, access elements of our simple vector class by using the square bracket notation. This again is sort of what I would call a wrapper over the vector class a little bit. We're kind of doing vectory things only in our own customized way. We've got a print function. And I guess that's it. It's a very simple vector class. Let's get to the hands-on. Page 1025. Yeah. All right. So if you like, you can take a look at the full simple vector class in the textbook files. Maybe we'll just kind of, now that it's all together in this file, let's take a look at it from the top down. So we've got actually a struct that's going to contain our exception handling for index out of range. So as you know, if you try to access an element of a vector that's too large or too small, you're going to get an index out of range exception, or certainly if you try to do that with an array. Here we have the class, simple vector. It is a template of class type T. So it's also going to create a pointer to an array of type T. Wrap your mind around that. Constructors, and here we're again overloading the square bracket operator. Down here is our constructor for our simple vector class, just doing some size setting and allocating some memory. Again, no concrete data types here except for S, which I think is, size. Otherwise, we're seeing lots of type T's. Here's another constructor. Here's our copy constructor. Here's our implementation of the overloaded square bracket operator. Okay? And here is where we're going to throw our index out of range exception if the user tries to access an index of our simple vector that is out of bounds. So we're going to check to see if it's less than 0 or if it's greater than the array size. If either of those is true, throw this exception and then return that APTR at location sub, where sub is the index that was passed. And then we've got a little print function down here. Okay, so that's the simple vector.h. In 1611 is where we're using that. Just some examples of instantiating some new simple vectors. Here's an example using an int. Here's an example using a double. Here we're storing some values, some arbitrary data going into our simple vector. Here we're displaying them. We're using the built-in plus operator on the array elements, displaying the values. Here in table, here's where we're using the overloaded square bracket operator. And we can also use the built-in plus plus or increment operator, printing things out. Everything works as we would expect. So member function definitions outside of a template class. So if a member function is defined outside of the class, then the definition requires the template header to be prefixed to it and the template name and the type parameter list to be used to refer to the name of the class. What that means, if you notice back here on simplevector.h, we've got basically, so it is a header file, but in this header file, we've got all of the header information and we have all of the implementation information. All that's contained in a single header file. What that slide was saying is if you would like to split this up, as we have done in previous lessons, if you want to split it up so that the header file is separate from the implementation file, like the header file is the header information in the header files folder, then the implementation is down here in the source files folder, you can do that with templates as long as when you go to do the implementation, you provide template class type T above the implementation, above that sort of method name, that member function name. You can do that just fine, just requires a little bit of extra syntax on top of it. No big deal. Talking about inheritance now, so class templates and inheritance. Templates can be combined with inheritance. You can derive a template class from a template class, just like we would be used to and expect. Other combinations are possible. You can derive a template from an ordinary class. You can derive an ordinary class from a template. Does not matter. Let's take a look at another header file here. I've actually got that pulled up. Searchvect.h. So searchvect relies on simplevector.h. So here's kind of a nested set of includes. So simplevector.h, what I always try to do is kind of, if I have a bunch of nested stuff going on like this, I always try to go back to the base level where there's no other custom header files being included here. These are all built into the language, but in searchvect, I'm including simplevector.h and then doing some of my own stuff. So searchvect class searchable vector extends simplevector.h, so we have to include it to be able to extend it. So we can extend that, and it is type T. We've got a constructor here, a copy constructor, and then an additional kind of convenience constructor. And then we've got our function called findItem. And the findItem function simply looping over the collection and returning if we found the item, otherwise returns -1. Takes a parameter of type T and searches for it within the array. And the key with this, I suppose, would be making sure that the data type that you pass in for type T is able to use the comparison operator. So if you pass in players, if you're searching a collection for a player object, you better make sure that you've overloaded the double equal sign, the comparison operator, in your player class. Otherwise, when you try to search it, it's not going to know what it means to have two players being equal to each other. And I don't necessarily either. That would be up to you as the programmer to define what it means for two players to be equal. Okay. So that's searchvec.h. And then the hands-on is where we'll wrap it up on 10/28. Finally, just using searchvec.h. Nothing terribly exciting going on here other than the searching, I think. Yeah, result equals int table.findItem. Okay, so remember that searchvec.h extends simplevect. So anything that you can do in simplevect, you can do in the searchvec. Searching, overloading, constructing, all that good stuff. Very good. Okay, so that is the end of chapter 16. What I would call it, as far as the templates go, some advanced level features and functionality of C++. If you've used some of the C++ STL, the standard template library, you should know that most, if not all of that code is written using templates. All of those standard data structures and algorithms can operate on a variety of different data types, not just ints, not just strings, not just chars, almost any kind of data. As long as you implement or overload the important operators, you can pass in whatever type of data you'd like to those standard template library data structures and algorithms. Looking at our list of topics here, we're nearing the end. We've got 1, 2, 3, 4 more lessons after 16. So next week's will be standard template library. So what I was just talking about, some of the built-in algorithms and data structures that rely heavily on templates. So it's good we talked about those this week to kind of get our feet wet with some of those ideas. We're going to be diving into the STL next week. We're going to take a look at in detail, some of those standard data structures like linked lists, stacks and queues, binary trees, good things that show up on programming interview questions, by the way. Okay, and these things definitely exist outside of C++ and are in all kinds of different programming languages. All right, with that, I'll say thank you very much, and we'll see you next time.